In the previous unit, we characterized the behavior at a minimum, and that would be that the derivative would be 0 in any direction, even in a function of many variables. Unfortunately, we know that even for a one-dimensional function, the derivative being 0 doesn't necessarily characterize a minimum, as illustrated by this function. So we need to put some more restrictions on functions such that minimums can be characterized as derivatives being 0. And that's where convexity will come into play. So convex functions are the focus of this unit. Let's start with functions of one variable. A function f, mapping real numbers to real numbers, is said to be convex if for any x and any z and any t between 0 and 1, f at 1 minus t times x plus t times z is less than or equal to 1 minus t times f of x plus t times f of z. Let's think about this just as a function of t. Imagine x and z are fixed. What this means is that as the argument transitions from x to z, that's at t equals 0 and t equals 1, the graph of the function, that's on the left here, must lie below the straight line which is connecting the points x f of x to z f of z. That's actually on the right as a function of t. Graphically, let's look at the function we examined earlier. If we pick this x and this z and draw the line connecting x, f of x to z, f of z, well, it's that red line. And the function does not lie below that red line for all values of t. This function is not convex. By contrast, here is a convex function. Notice that if we pick any 2 points in the domain and draw a line connecting the graph at those 2 points, the graph of the function always lies below this straight line called the chord. I'll do that in 4 separate cases. And we can see that in every case, the function lies below the chord. This is a convex function. Convex functions do have the property that the minimum is completely characterized by the derivative equaling 0. Consequently, one approach to minimize a convex function is to set the derivative equal to 0 and try to solve that condition. For functions of many variables, the definition is exactly the same. The function f, mapping an n-variable vector to real numbers, is said to be convex if for any n by 1 vector x and any n by 1 vector z and any scalar t between 0 and 1, f of 1 minus tx plus tz is less than or equal to 1 minus t times f of x plus t times f of z. Again, this simply means as the argument moves from x to z, really t transitioning from 0 to 1, the graph of the function lies below the straight line connecting the points of the graph x f of x to z f of z. It's easiest to visualize this in MATLAB both for a non-convex function and for a convex function. Let's do that. Here's a function of 2 variables, x1 and x2. The function is graphed vertically. It's clearly non-convex. Let's see that in terms of the definition. We'll pick 2 random points, draw the chord, which connects the 2 points on the graph, as well as the function along the surface. The surface is graphed in red, the chord is graphed in black. As t transitions from 0 to 1, or in other words, as we move from one point to the other point, the value of the function along the surface does not lie below the chord of the function. Consequently, this 2-dimensional function is not convex. Let's try some other points. There the function lies below the chord. This one it doesn't. There it completely doesn't. The function lies above the chord at all times. Another one. Another one. This function is obviously not convex. Now let's visualize the same process for a convex function, which is shown right here on the left. Pick 2 points, draw the chord connecting the points, and the function value along the surface. It's displayed both on the left and the right. Clearly, the function lies below the chord. Let's try a different set of 2 points. Again, the function lies below the chord. Let's try a different set. The function lies below the chord. A different set. Function lies below the chord. I'll do this several more times, and in every case we'll see that the function does lie below the chord. If that's true for every possible pair of points, then the function is a convex function. Geometrically, you want to think of convex functions as bowl-shaped in a very general sense. So we visualized both convex and non-convex functions and have some experience with what the meaning of this definition is, that between any 2 points, the function lies below the chord connecting the 2 points. We saw that for functions of one variable, the derivative being 0 completely characterized the minimums of convex functions. Well, the same thing holds for convex functions of several variables. Intuitively, it's clear from the graphs we've drawn. A convex function has a minimum at a point x bar if and only if the derivative of that function at x bar equals 0 in every direction. Ultimately, we'll use this to understand how to solve these least squares problems. But first, we need to show the convexity of the function that's involved in least squares problems. Let's do that. On this slide, we pose the question, is the norm of ax minus b a convex function of x? Let's check. Denote the function f of x as the norm of ax minus b. Now we simply need to check the condition. Let's let x and z be arbitrary n by 1 vectors and t any scalar between 0 and 1. Then evaluate the function at that combination of x and z. Plugging in what f is, the norm of a times the argument minus b, gives a times the combination of x and z minus b. The first thing to do is to replace the 1 times b with 1 minus t plus t times b. That's all that's happened in that equation. Notice that that's just a 1, so we haven't changed anything. Now we can group the 1 minus t terms as well as the t terms. Notice there's a 1 minus t on the a times x, and there's a 1 minus t on b. Similarly, there's a t associated with the az, and there's a t associated with the b. So group those, and that's what's shown here. A times 1 minus tx minus 1 minus tb plus a times tz minus tb. The t and the 1 are scalars. Pull those out of each of their respective terms and group again. 1 minus t pulls out in front of ax minus b, and t pulls out in front of az minus b. This is looking good. Now apply the triangle inequality. Remember that the norm of the sum is always less than or equal to the sum of the norms. That gives us a less than or equal sign. Now we'd like to pull out the scalars 1 minus t and t. Normally that would involve an absolute value. When you pull a scalar out of a norm, it becomes the absolute value. But remember that t is between 0 and 1, so t is non-negative, and 1 minus t is non-negative. So when we extract those scalars from the norm, they already are non-negative numbers, and we don't have to put an absolute value there. Therefore, this is exactly equal 1 minus t times the norm of ax minus b plus t times the norm of az minus b. And again, that works because t is between 0 and 1. This is precisely 1 minus t times f of x plus t times f of z by definition of what f is. This shows that the norm of ax minus b, regardless of a and regardless of b, is a convex function of x. It really has that bowl-like character as shown. So the answer to our question is yes, it is a convex function. In the next unit, we'll use this to derive the conditions for solving the least squares problem.